I am Paramita Kole. Today I am going to present my work titled Differential Change Point Detection in Marked Temporal Point Process. This is a joint work with Harshavardhan Alimi, Shreya Shingla, Shorangshu Bhattacharya, Nilay Ganguly and Abir De from IIT Kharagpur, IIT Bombay and L3S Leibniz University, Hanover, Germany. Modeling temporal systems are important because temporal systems have application in many critical applications like emergency healthcare, weather forecasting, earthquake prediction. However, temporal system often undergo significant changes. For example, air pollution data. As you see from the image, after the year 2003 March, it suddenly reduces. Tweet data. We can see that after Israel announces ceasefire, the number of tweets on this topic suddenly increased. In earthquake data, we observe that after the year 2008, suddenly two new zones of earthquake appears which was not there before. So we see that uh, temporal distribution changes, and change point is a point in the sequence where the underlying distribution changes. Modeling change points are important for modeling temporal sequences properly. In our work, we address the problem of change point detection in asynchronous temporal sequences. Asynchronous temporal sequences can be modeled by temporal point process. So here we have discussed approach to for change point detection in temporal point process. Change point detection is well studied in literature. However, most of the methods are targeted towards change point detection in time series data. There are many methods like histogram based method, kernel based method, Bayesian method and many others. However, they do not extend easily to temporal point process or temporal asynchronous sequences. There are some methods for change point detection in temporal point process. They are very sparse and most of them suffers from many shortcomings. For example, often they assume prior knowledge about the pre and post change point distribution. They are often designed to detect single change point from sequence. Often they are window based. That means while detecting the change point, often they lack the global view, which is not good for multiple change point detection. And generally these methods perform model selection and change point detection in a disjoint manner if they do not assume that distribution is known a priori. In our method, we have proposed a change point detector where we have tried to overcome these shortcomings. For example, our method can detect multiple change points in sequence. It do not assume any prior knowledge on the distributions, model distributions. It performs model selection and change point detection in a disjoint manner, and it detects change point based on a global view, that is, it checks the entire sequence for detecting the change point. Now I will present my method. So suppose there is a single change point in a sequence. Given a sequence, there is a single change point in the sequence as marked here by the red dot. So how we can retrieve the change point? Suppose the left side events are sampled from distribution theta 1, whereas the right side points are sampled from distribution theta 2. So we can say that for the right side events, their likelihood under theta 2 is greater than their likelihood under theta 1. So we can see that if we take for every point, if we take sum of log likelihood ratio of the events for theta 1 by their log likelihood of theta 2 by theta 1, then mm, that will be positive for events on the right hand side and negative for the that will be greater than 1 for event on the right side. So we can say that we can detect the change point by finding that point from where to the end sum of log likelihood ratio will be maximum. This is a known technique known as generalized log likelihood ratio testing for change point detection. However, it assumes that we know the model distribution a priori. However, sometimes we do not know the model distribution beforehand. Existing solutions often perform model selection on windows before change detection in that case. We propose a joint method where we perform model selection and change detection in a simultaneous manner. So as we see in our proposal, we have proposed a bi-level optimization problem where first we fix the change point at some point k star, and then for events before k star we learn the model parameter theta 1, and for events after k star we learn another model parameter theta 2 that we do by maximum likelihood estimation. Now after fixing theta 1 and theta 2, we find the change point k star from the data by log likelihood ratio testing. So we proposed a bi-level optimization problem where in one step we perform model selection and in another step we perform change detection. If we do them in alternating manner, we will reach a solution. However, let us see whether it converges to some optimal solution. Consider an alternative formulation where we are optimizing over change point location and model parameter at the same time. This is a joint optimization approach. That is, we are as change point, we are selecting that location for which corresponding partition have maximum total likelihood for corresponding optimal model. This problem is, so we can show that at optimality the solution of our bi-level optimization objective and the optimal solution of this joint optimization problem is actually same. Therefore, however, the joint optimization problem is difficult to solve. Therefore, in our work, we will be solving the bi-level optimization problem. In our bi-level optimization problem, can be extended to multiple change point also. For example, suppose the sequence is consisting of 3 partitions. The first partition, the events are coming from some distribution theta 1. Second partition, events are coming from some distribution theta 2, and thirds are coming from theta 3. How we can extend our bi-level objective to this multiple change point setting? There are 2 change points in the sequence. So for the model selection part, what we can do, for each partition we add one log likelihood term. As we see the model selection part, there are 3 partitions, and for each partition we learn model parameters separately. Moreover, we modify the change detection step by adding one term for detecting each change point, and we detect each change point by considering log likelihood ratio of the model parameter of the post distribution by model parameter of the previous change distribution. However, our model selection problem is a continuous optimization problem, whereas our change point detection is a discrete optimization problem. So now we want to relax the discrete optimization problem into a convex form. How we can do the relaxation. Let us consider the single change point case. Suppose in the given sequence, J1 star is the change point. Now consider an alternative vector representation of the J1. Let us set all the points before J1 to 0 and all the points from J1 to 1. Also consider two additional vector representation, A0 as all 1 and A2 as all 0. Now consider the convex relaxation that we have written here. If you consider the leftmost term of the convex relaxation, the term basically is equivalent to the model selection part for the first partition in our discrete optimization problem, because A0i is all 1 and A1 is 0 only for the first partition. Therefore, A0 minus A1 will actually denote the first partition, of the sequence. Similarly, if we consider the second term in the model selection part of the relaxation, A1 minus A2 basically denotes the second partition. Therefore, we can see that in the model selection, our proposed convex relaxation for the given configuration of A0, A1 and A2 actually reduces to our previous bilevel objective problem, their corresponding model selection part. Now let us consider the change point detection part. In our convex relaxation, the change point detection part, if we replace the A1 variable by the given A1 star configuration, it actually reduces to the discrete change point detection part in our previous bilevel optimization objective. Therefore, you can see that at least for one convex solution, the given convex relaxation is equivalent to the proposed bilevel objective. As our given problem is a linear problem, so for at optimality, for every fractional solution there will be one integer solution, and we can show that at least we have shown that at least for at optimality corresponding to every discrete solution there exists a corresponding continuous solution. So we can say that the convex relaxation will actually reach the same optimality as the given bilevel discrete continuous optimization problem. So now we write our convex relaxation in a more general form where we consider multiple change point case. So now we can solve this convex relaxation in a iterative manner, where for model selection we perform gradient computation on the model parameter theta, and for the change point detection we find the parameter matrix, we find a star variable by solving linear programming on the second part of the problem. So we alternatively perform model selection and change point detection, and gradually we reach the optimality. So we call this algorithm as differentiable change point detector or DCPD. However, DCPD does not scale well because for detecting every change point it checks the entire sequence. Therefore, it is not scalable with respect to the number of events in the sequence or the number of change point. Therefore, we propose a window-based extension DCPD W. What it does, it splits the entire sequence into many overlapping windows. On every window, it applies DCPD to find a local change point from every window. It weights every change point by their log livelihood ratio score, and finally it selects top k change points with maximum score. This method scales well with respect to DCPD later we will see that for that it incur minimal drop in accuracy. Moreover, this window-based method works well because long-term dependencies are weaker than short-term dependencies. Now we validate our algorithm on multiple real-world datasets. For example, earthquake, particle, Chicago, rat. Earthquake dataset contain seismic event. Particle dataset contain events of finding radioactive particle in some beach. Chicago dataset contain crime event, and rat dataset contain neural spike train events. Now we show the results where we compare our algorithm with three window-based baseline. We report normalized mean detection error to measure performance of the algorithm, and we validate our algorithm on 6 real-world dataset. Here we see that for most of the dataset, DCPD has been able to manage superior performance than other baseline. DCPD is of course inferior in performance, inferior to DCPD. DCPD window is inferior to DCPD in performance. However, it generally manages to stay second in position. GLR Hawks is best among the baselines. Also, we compare the score returned by DCPD window with other window-based method by plotting their ROC curve, and there we find DCPD window to perform comparable with other baseline, even sometimes better than them. So we conclude our presentation by summarizing our work. We have proposed DCPD, a differential change point detector for asynchronous temporal data. DCPD proposes a novel bi-level formulation to combine change point detection with model selection. Also, we propose DCPD window, which is an immediate extension to window-based approach. DCPD window combines precision of DCPD with scalability of window-based methods. Finally, we test both of our algorithm on various synthetic settings as well as multiple diverse real-world datasets.